Good morning, everyone. So let's start today's lecture. We are going to discuss about the asymptotic analysis of algorithms, right? Okay. So this is the first lecture on analysis of algorithms. I hope you can hear me. If one of you can, like always, can write down yes or no, that will be quite helpful. Okay, thank you. So, analysis of algorithms is one of the very important topics in data structures and algorithms. And in general, also, when you write down a program, there must be a methodology to find out whether your program is good enough or not. Good enough in the sense that whether it is utilizing the space optimally and the time of execution is optimum or not. There is a possibility that the program which you have wrote down is maybe not up to the mark when it is compared with other algorithms. So for example, you go and join a company and they ask you to write down a program to perform task X, and the amount of time your program takes is say 2 hours, right? And the person who gave you this assignment, he says that actually the program which we already have takes only 2 minutes, right? So there is some problem with your program. Now we must have a methodology to find out these timings. This is called as time complexity. We will see very soon. But the whole point is that with the help of analysis of algorithms or by calculating a specific type of variable, we will be able to find out whether our algorithm is good or not, or we can optimize it further or not, right? Okay, so let us start. What first question is, what do asymptotic notations do? So asymptotic notations are the languages which allow us to analyze an algorithm's running time by identifying how it is behaving with respect to the input size, right? So, in this whole definition, the most important thing is the input size, right? I will reiterate, it is a type of, it's a way to which allows us to analyze the algorithms running time, right? Algorithms running time. And how do we analyze the algorithm's running time? We check its behavior with respect to the input size, right? When the input is increasing, how our algorithm is going to behave. This is also called as algorithms growth rate, right? Growth rate means that as input increases, how your algorithm is behaving. Or we can say that it is a measure of how an algorithm is going to scale when we look at the input size, right? We know that input size increases over the period of time. So, for example, you run your program for one input, then you run your program for two inputs, then you may run your program for 100 inputs, then maybe 1,000 inputs, and then we have to see how our algorithm is going to perform when we scale when we increase the input size, right? Their exact running times, right? It is, we should remember that we are just checking the rate, right? We are not looking at the exact running time, right? This is not what we are looking forward to. Because exact running time depends on many things. Can you name one or two maybe? That will be helpful. Exact running time of a program depend on what? Depends on what? So, for example, if I have hardware, yes, system configuration, absolutely right. So, it depends on many things, hardware, or we can call it the system configuration, which includes computer processor speed and so on and so forth. So, actually, the same algorithm can take 2 minutes to run, and it can also take 2 hours to run, depending on what type of machine we have. So when you go and join some place and somebody asks you that your algorithm is taking 2 hours, somebody else is taking 2 minutes. Why? Obviously, now we can see that the answer does not remains. I mean, this quantity cannot answer to this question, and the reason is yes, processor clock speed also. And the reason is because this time depends on many things. For example, maybe the machine which person gave you is a very old machine and everything is like kind of slow, and this guy is running on a state of the art machine and everything is very very fast, right? So these comparing the times is not a correct way of comparing two algorithms. Therefore, we need something else. And that something else is that how our algorithm scales with input size, right? So this is what we should use. Is it clear to you why the running time in terms of time is not the correct measure? Right, running time depends on the number of operations we have to perform, and it also depends on the computer instruction set and so on and so forth, right? So even if you have a very simple code, the different type of computers are going to take different amount of time. So we are not interested in minutes or hours or days or weeks or something else. We are interested in how this is going to, how our algorithm is going to scale in relation to its input size. Now, this whole analysis of the algorithm's running time with respect to its input size is called as asymptotic notation. So this is what we are going to do. Asymptotic notations are used to measure complexity. So this complexity is not going to be only in terms of time, right? It could be something else also. For example, resources which are required, as such as, for example, space on the call stack. So this is called as space complexity. When your program runs, how much amount of space it is going to need, and what is the time complexity. So with the, this used to be very important consideration in yesteryears, when memory was really very very expensive. But now memory has become quite cheap. So although it makes a big difference even now, because if we look at the kind of data sets which we have to utilize to run our AI program, database programs, then space complexity nowadays again started playing a very important role. But time complexity remains very important, because if your program is not optimized for growing input size, then the time it requires to execute is going to be far more. I mean, it is going to increase with respect to the increasing input size. So let us look at try. I think I lost the connection somewhere in between, right? So anyone of you who can tell me where we lost each other? So we were discussing this. I believe you got it. What is time complexity and what is space complexity? Yes or no? Maybe you can write down in the chat. Can you hear me? Okay, all right. Now I got the message. Yes, space complexity. All right. So space complexity is the amount of space which will be required to while we in as the input size increases, how it is going to make a difference on the amount of space which is going to be required. And time complexity is when the input size increases, how is it going to make a difference to the time which our algorithm is going to take to execute that particular program. All right, so let us look at one Python example. Uh, this particular program is going to print values for x between maybe 1 and 10. And so this requires to run 100 loops. And best of three, the time required is 11.1 millisecond per loop, right? At the same time, when we run this program for 1,000 times, the best of three is 1.09 millisecond per loop. So you can see that, sorry, this is 10. This is, when we run it for 10 times, the time required is 1.09 milliseconds. So you can see that whatever this program is doing, as we increase the input size, initially it was 10 inputs and then we had 100 inputs, the time required has increased, input size increased by 10 times, right? And processing time also increased approximately by 10 times. So this means that our algorithm is linearly increasing with respect to the input size. As input size increases, the time required to execute our program is also is increasing in the linear fashion, right? We can do so in C and C++ also by using this .h file, right? We discussed what .h means. Can you quickly tell me what does it mean by to have a file .h? .h means what? Like .c is a C file, .h is header file, yes. So we have called a header file time.h, which is going to tell us that please call time function and utilize it while we run our program. So the whole point of this example is that it tells us that as the input size increases, the time of execution is also going to increase. We will soon see how we are going to depict it, whether it is good or not, and so on and so forth. There is also a possibility that irrespective of, so over here, as input size increases, the execution time is also increasing, right? There are certain programs where as the input size increases, the execution time remains the same, or it can also increase exponentially, right? So there are multiple possibilities. This is one of them where input size and execution time remains the same. We can also have input size increases, but execution time remains the same, or execution time is going to increase exponentially. So don't worry about any of them. We will discuss one by one, right? But the point is that in this particular case, the time was increasing linearly as we increase the loop. So let us look at one very important type of algorithm, which is generally used in many scenarios, and it is called as binary search, right? We know that, for example, if you want to search something in a dictionary, right? Dictionary. Oh, here it is. Oh, something in a dictionary. So how do you do it? How do you find out something in a dictionary? Suppose we want to find out the meaning of word DICT, right? So what do? We have a dictionary. We are going to go right in the middle of the dictionary and see which side D is. It's on this side. We go right in the middle. We go this side. We go right in the middle. And over here, we will be able to find out the word DICT, right? Somehow by doing this process over and over again. This is called as, so what we are doing, we are dividing the whole space search space. This is called as the search space. This thing is our search space, and we are trying to search in this search space. And what strategy did we took? We divided first into two parts, right? So this, for example, we can call it side 0 and side 1. Then we are going to divide this again. We are going to call this side 0 and side 1. We divide it again. We are going to call this side 0, side 1, and so on and so forth. So we can see that every time we are dividing our search space into two parts, right? And then we are trying to search whatever our query is. In this case, the query was ticked, and therefore it is called as binary search because we are dividing the search space into two parts. Similarly, when we try to find out a phone number in our phone book, which is like a same as a dictionary, all difference is that in place of these all possible uh, English words, or if it is an English dictionary, or Hindi words, if it is a Hindi dictionary, and Punjabi words, if it's a Punjabi dictionary, French words, if it's a French dictionary, and so on and so forth. In phone book, we are going to have names, right? We'll have names, and then similarly, we can divide and search and find out where a particular name appears, and then we will be able to do it. So these type of searches are called as binary searches, and we will look at this example, and we'll try to find out uh, how to analyze this algorithm as we write it down. Any questions? Did you get what a binary search is? We have a search space. We divide it into two parts, and we further, if for example dict is there, so we divide it into two parts. We try to find out on which side it is lying. If it is lying on this side, we again are going to divide it, and we keep on dividing this. So the question is, till when, till when, till when should we keep dividing the space? Any answers? Till when should we keep on dividing the space? Anyone?
So till our range becomes one element.
Absolutely correct. Till our we reach to the word which we are searching for. So we are trying to search for dict. So we'll keep on doing it unless we reach to the place where we have got DICT. And same with phone numbers also. Suppose you want to find out somebody's phone number, our phone is going to search the space unless and until he or she reaches to that particular value. Perfect. So this indicates that nobody is asking a question and you answered to the question correctly. Three of you have wrote down on the chat also. So it indicates that all of us found out how binary search is going to work. All right, so let's move to the next thing. So binary search is an algorithm, obviously, with sorted list of elements. Now, this is extremely important part in binary search, right? If, for example, I say that I will give you a dictionary, right? You have a dictionary, and all words are placed randomly, right? If this is the case, then what is going to happen? Anyone? And we
सर
are
चलेगा कि आगे मूव करना है या पीछे मूव
right.
करना है किसी पर्टिकुलर वर्ड.
Absolutely right. So we have the same dictionary. We cannot divide it into two parts because we don't know where the word is going to be. Everything is randomly placed. So we have to look at the first word, then second, third, fourth, fifth, sixth, and keep on doing this unless and until we reach to the last one. If, for example, dict is placed over here. So while we perform this binary search, what we have assumed that underlying values are already sorted, right? So if, for example, somebody asks you a question that I would like to do a binary search and I have some search space or some values, please write down an algorithm. So your first question should be, are the values sorted or not? Because the binary search can run if and only if the values are already sorted. Correct. So here is an example where we are trying to find out Cramerica Industries in a dictionary, and we found out that this entry, this is a phone book, this entry is over here, right? So our binary search algorithm is going to do what? So this is the execution of binary search algorithm, right? So can you tell me what our binary search algorithm doing? It will take the query and it will execute the program, which is, for example, in this case, is a phone book, and it will try to find where it is, and it is going to give us a particular location where that particular thing lies. And for example, in the same book, we try to find out Vanderlei Industries, and it is not there. So we'll get null. Null is going to indicate that there is no such entry, right? There could be only two possibilities: either we find it or we don't find it. So, in case we find it, our binary search algorithm is going to return the position where that particular value lies, so that we can access it as and when it is required, right? Does that make sense, that a binary search algorithm is going to work like that? Right? So binary search is going to either return us what we have, or it is going to tell us that it is not there. Sorted means ascending or descending order, right? So the one question is that when we say sorted, do we mean ascending order or do we mean descending order? This question is very important. And the reason is, I said that, if we have a dictionary, we divide, and dict is we move in this side, right? So I assumed that it is in ascending order. So which means that starts from A and ends with C. But that may not be the case, right? There is a possibility that dict could be over here. So what you have asked is extremely important. And therefore, we also provide an information to binary search whether keys are in increasing order or they are in decreasing order. We have to give that information. If we don't give that information, that our algorithm must first check any two keys and find out whether they are in increasing order or decreasing order. And once our algorithm checks and finds it out, then we can move in this direction or in that direction, right? Does that answers to your question? All right. Okay. So this was, thank you for pointing it out, because it's very important. When we write down an algorithm, we must understand whether it is in decreasing order or increasing order. Then only we can execute our program. All right. So let's move to a question. Everyone, please beware that we are going to have a question now, which you have to answer. Oh, sorry. Yeah. sorry. Yeah. Suppose you are looking for a word in a dictionary, and the dictionary has 2,40,000. This is a T over here, but I think I make it. Sorry. Yeah. The dictionary has 2,40,000 words. In the worst case, how many steps do you think each search will take? Each search means, suppose we want to find out a word over there. Let me just, so that you can concentrate on your work and not on this. This is a very good book. I will show you. You can have a look at this book, and it's really amazing to understand some of the concepts. It's not very deep and detailed, but yes, it will give you an idea about how various algorithms work. So the question is that if we have a dictionary with 2,40,000 words, and suppose we are trying to find out the word, uh, if this word exists, right? This is going to be the worst case, and the best case is going to be A. So the question is, how many steps do you think each search will take in the worst case? In the worst case means that every time you search, it comes out to be the last word. So how many steps will be required? Yes,
18.
I have already started. Please write down in the chat, so that others can also try. Yeah, I have got one answer. Please quickly calculate, and so that we once we have 4 5 answers, then we will start understanding. So we have. I will start writing down the answers so that all of us can have a look. 18, 18. 240,000 searches, 18 searches. There are only four. I need one more, and then we are good to go. Okay. So many more 18s. All right. Now, we are not in class, otherwise, I would have asked for help from one of you to tell us why they are 18, right? So, since we are not there, so we'll take another approach and we will try to understand why they are 18, right? So, the advantage of online learning for you is that you don't have to answer too many questions. Although this is only an advantage from the point of view of not answering the questions, but it always helps when you answer. It keeps you first of all awake, eyes wide open, and your mind working all the time, which is again also good. So that is why I ask you to write down answers. But even after asking for infinite amount of times, what I received is only 9 answers, which means that a lot of people are still in the sleeping state. Anyway, this is not a preaching class. So all right. So the question is that we have 240,000 words, right? And we are doing binary search. So what we are going to do, first of all, we are going to divide the search space into two parts. So we'll have 120,000. This is our first step. Then we will have 60,000, right? 60,000. That will be our second step. Then we'll have 30,000, 30,000. That will be our third step. Then we'll have 15,000, 15,000. That will be our first, second, third, fourth step. And then we'll have 7.5 thousand, 7.5 thousand. That will be our fifth step, and so on and so forth. So I will not write down this. These many are not required because I have the picture here. We'll look at the picture. Here it is. So we have 240,000 values, and then they in the next step they become 120, then half 60, then half 30, then half 15, then half 7.5, then 3750, this blah blah, and finally we get the idea, right? We get to the correct word, and if we count them, they are going to be 18, right? uh, right? You counted them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. On 18th step, we got the answer. So this is how this binary search is going to help us in finding out the correct answer. So one of the answers was 240,000, right? That answer is wrong because we have specifically told that we are going to use a dictionary, and dictionaries are always sorted. Now this is wrong, but at the same time this answer could have been right also, right? Under what circumstance did could this answer had been the right answer? Any answers to this question? So this is wrong. One of us told us that this could be an answer. In the current situation, it is not correct because we already told everyone that it is a dictionary. Now, under what circumstance, and if we are using binary search, this could have been the right answer. Yes, so we got many answers. Very good, excellent. Random order, if it is unsorted, If we do linear search instead of binary search, all of these answers are right. So this answer could have been right if in place of having a dictionary, we had some jumbled words, so we have to search everything. And since we have to search everything, the algorithm which we are going to use was going to be linear search algorithm. So either we use linear search algorithm, or if things are not sorted, then it, in the worst case, it would have taken us 240,000 calculations in the worst case. In the best case, how many calculations would have been required? So this is the worst case, right? One. Absolutely right. One, why? Because everything is random wherever we start, and if we are lucky, we could have found the correct value right lying there. So this would be, answer would be one. Very good. All right, so let us move to the very important next slide, which is, so you have, all of you have understood, right? Now I'm going to, okay, any questions? I forgot to ask. I think there is a question. Won't A also be worst case as ZZ? In what, in which case? A also be worst case as ZZ, right, it could be. So I got your question. This, I said that this could be the worst case if our dictionary was in place of ascending order, wasn't ascending order. But dictionaries are never like that. They are always in ascending order. It always starts with A and ends with C. So is this, am I right in understanding your question? Or if maybe you can write down another line or speak or and tell us. Okay, all right. So this is what, so A could had been the worst case, but we know that dictionaries are always ascending. So this is going to be the best in the sense that if we are not using binary search. If we are using binary search, is it does not matter whether we are searching for A or we are searching for Z. If we are using binary search, A and Z, both of them will appear at the end, right? Because we start in binary search, we start in the middle, and then slowly we move towards the end. So Z as well as A, both of them are the ends of our search space. Therefore, irrespective of whether we are searching for A or we are searching for Z, it is going to take the same amount of time, because we start from not right at the start, but we start at the middle, right? And therefore, these distances are same. Therefore, the number of steps are also going to be the same. Does that answers to your question? All right. Perfect. So now we'll move to our next friend, who is an algorithm. So what we are trying to do, we are trying to understand how we can implement. Know that if you want to write down an algorithm, generally we first create something which is called as flowchart. So this is a flowchart. Once you have the flowchart, things become easy, because we know where the decisions are going to be taking. So we can put decision boxes there, and then later on in the program we can utilize them. So let's look at this program. Okay, we have an array A with attribute key. Attribute key means the value. We can, oh, sorry. With an attribute key. Attribute key means the value which is stored at that particular position. We have elements 1 to n ordered on the values of key, so that here it is. So we know that our space is in ascending order or descending order. One is least, then two is greater than the first one, third is greater than the second one, and so on and so forth. So this array A is going to be an ascending order array, right? And elements are stored 1 to n, ordered on the values of the key. So, for example, if we would like to, yes, I have two chats here: ascending order, ascending order. Perfect. Good. So, we are going to. So now let us look at this algorithm and try to understand what we are trying to do. So what do? We first of all, we initialize a variable L, and we say that the value of L is equal to 0. And we initialize another variable R, and we say its value is n plus 1. Now, the key which we would, or the index we would like to find uh, in such a way that its key value is x, right? So what are we trying to find out? We are trying to find out the position where key x is stored, right? So it means that we have to probe this location where value x is stored. Now, how do we do it? As we just discussed in binary search, we start doing things right in the middle. So we first of all, we set the position at the middle of both of them. So we say R minus L by 2, and this is the value of P. Initially, the value of L is going to be 0, so we'll have R by 2, and we'll start from here. Now, we will first of all try to find out whether we have found this key or not. If uh, P is equal to 0, when could P be equal to 0? If R is also equal to 0, right? So we can take a lower bound over here, and if it is equal to 0 and the value of key is not x, we will say that exit and the value is not found. But if the value of P is greater than 0, then what are we going to do? We are going to take another step, and then we will try to find out where that particular key is. Okay. How are we going to do it? We are going to update the value of P. So now P will become L plus P. L plus P means L was initially 0. So till now, this value is equal to 0. And the value of P is the half value. So this now value of P is updated to the mid position in our binary array. Right now we are going to, and we know that it is in ascending order. So our array is already sorted. It's a sorted array. So we compare key, which is right in the middle, this key with x. And if our key is less than x, which we have found out at this particular location, then we will say that it's in ascending order, and what we are searching for is less than what we have found over here. What we have found over here, it is less than that, therefore we are going to move in this direction, right? So we take this decision path. Whereas if, for example, we say that our key is greater than what we have found over here, then we have to move in this direction. So we take from decision boundary, we take this path, right? And we are going to update the values on the basis of which path we take. If we are going in this direction, then L becomes P, which means L was initially 0. So we say that L is this space. Otherwise, R becomes P, which we are going to say that the R's position, which was initially n plus 1, is equal to now the central location. So this will help us whether we are going to move in this direction or this direction, and we perform these operations over and over again until we either reach to this situation where P becomes 0 and we say that the value is not found, or we found the value of x and we say that the location where we have found out the key is this. Now the question is, yeah, I will take just 1 second. I will take that question. So this is what happens in this algorithm. So what I'm going to do is I'm going to show you the complete algorithm, and please have a look at it. By the time I will read the question which one of us has raised: if we have similar values in our data set, will binary search be effective as linear search? All right. So the question is that if, please tell me if I understood your question correctly or not. If not, you can always write it down. The question, it seems to me, is that if we have an array and all the values are same, all the values are same, uh, will binary search be effective as linear search? Will binary search be, so the question is that if all the values are, for example, 1 over here, and we are trying to search value 1 with the help of binary search, and if we do it with the help of linear, my writing is not that beautiful, uh, with the help of binary search or linear search, the question is that will it make any difference whether we use binary search or linear search? Is this what you are asking? Am I right in interpreting your question? Okay, so this is not the correct question. I will answer to this question first, and then I will go back to what you have just said. So, in this case, both of them will take the same time, because the reason is that all the values are same, and right at the first instance, you will be able to find out whether it is there or not, or you will never be able to find out whether it is there or not. So if we already know that everything is same, then binary search is going to divide and move and divide and move. So binary search will take less time than linear search, because linear search has to, no, sorry, right at the first instance, both of them will give us the answer that one has been found. Now, actually, the question was not this. So let's look at the question, what the question was. Okay. So the question is that if we have, say, 5, 6, 10 elements, and 3 elements have same value. So the question changes a little bit. The 1, 2, 3, 3, 3, 3, 4. If we have this type of an array and we try to utilize one of the searches, will binary search and linear search take same time or different times, right? It depends on many things. Is it right? Now, am I right about the question? Yes, all right. So this depends on many things. For example, if we are searching for 4, right? In that case, binary search will take less time and linear search is going to take more time because it is over here. And binary search will divide and quickly search for it. Whereas if we use linear search, it has to start from here and slowly go to reach this place. Similarly, if we are searching for example, value 1, then also binary search is going to take less time. But your question obviously is, what if the value which we are searching for is 3, right? In this case, it depends on where it lies. So 3 is going to lie over here. Binary search will be first one to reach to this place, and therefore will find out quickly. But we do not, we do not write down algorithms in such a way. We are going to look at the worst case, and worst case could be that this is the algorithm and 4 is the value which we are looking forward to. Since we are looking forward to this value, binary search is going to take less time. Therefore, we will choose binary search over linear search, because we know that as this grows, right, if we have in place of 4, if we have 2000 elements or maybe 10,000 elements, and we are searching for the last element, then what is going to happen? In this particular case, when we are searching for the last element, binary search is going to take less time. So as the input grows, binary search is going to take less time. Therefore, its time complexity is going to be lower than the time complexity of our linear search algorithm. Right? Does that answers to your question? Quickly write down yes or no, so that we can. Yes, but what if we want third 3? All right. So right. Next question is, what if we want third 3? There is no way to differentiate between third 3 and this 3, right? till the time we have one dimensional array. This three and this three are same. So if, for example, I ask you tree, then you can give me any tree. If I ask you that you have to give me Gulmohar tree, then I have defined, and therefore, so this is going to be a two-dimensional search space, tree and a specific type of tree. But in this case, when we have an algorithm, so first, third, and third are same. In a dictionary, if we write down that I would like to search for exit word, and the dictionary guy enters exit word 100 times, it does not make any difference till the time all the definitions of these exits are same. Does that make sense? All right. So it answers to your question. All right, perfect. So let's move ahead, and I think we have left with 1 or 2 minutes. So quickly, we'll try to quickly finish it off. I mean, I don't want to finish it, but we just have to look at this program. Here is the binary search program. We start with as you know from our previous discussion of the uh, the the flow chart. We have one variable low started with 0, high variable length of list -1, and while low is less than high or equal to, we assign a mid value. Then we guess is that list at this position, what is the value. Then we try to find out if this is equal to the item which we are searching for or not. If it is equal, we say that it is lying in the middle. If it is greater than item, then we move towards higher side. We change this value, and otherwise we move in the lower direction. And then if nothing happens, then we are going to return a none. So we will test this, but time is up, and I think you may be having another class. So we'll meet on Monday, and then we'll have a look at this particular algorithm. Right? Any questions or answers or doubts or anything? No. All right. Okay. Thank you.